Hello everyone, my name is Andres Blanco and I'm going to talk about my work on 802.11 complexity. This is based on some work I've been doing the last couple of years and the analysis of iOS and Android platform and some bugs I found during this research. First, I'm going to tell you some motivation that I have to do this research. The first one is that nowadays 802.11 it's everywhere. You have it on your printers, on your refrigerator, it's everywhere. So these chipsets that handle all the protocol, they are everywhere, so it's a nice target. The next thing is radio frequency has not defined boundaries, so maybe you put a wireless network inside a building and usually you can access or is reachable from outside. So it's something you need to take care about it, because if not, attackers could access your network. So as you can see here, we have a lot of different standards that are developed by the IEEE, and next year, I think 802.11 is going to turn 20 years old. So a lot of changes have happened on the protocol. So every time it's getting even more complex. And not only the IEEE add features to the protocol, but the vendors. Also vendors develop their own protocols, proprietary, or extensions, or different, I forget the word now, but we're going to see now some examples of this. And finally, one thing that usually people they don't analyze too much is that nowadays devices have different modes. So your phone can turn into a hotspot, or can be a peer-to-peer device, or it can be a normal station, or can do a mesh network. So nowadays the protocol is turned so complex and has a lot of features, and these features are usually inside the device, inside a chipset in your phone, inside a chipset on in your printer. So maybe you don't use all these features, but these features are there. So attackers can abuse them or use to access your devices. So to start talking about a little introduction of the protocol, I'm going to start talking about the frames. So we have three types of frames: management, control, and data frames. In this presentation, I will be focusing only on management frames, okay? Two of the most common frames that are used all the time, they are the beacon frame and the pull request frame. The beacon is used by access points to announce a network. So every time you're scanning networks, beacon frames are on the air, and they give the capabilities of the network. So the device that wants to connect to it can know if they have the same specifications or the same features that they need to connect. And the pull request is a frame that is sent by stations all the time to see if the networks are reachable and they can communicate. So this is the association process, okay? And this is done every time you want to connect to a network. And an important note here is that I'm putting here the authentication frame, but it's important to notice that nowadays on the protocol, that the authentication frame is not used for authentication, okay? If you're using WPA or WPA2, authentication is done with data frames, and after the association was already done. So any station can associate a network and don't send not even one data frame, but they can associate. This is important because when I'm going to explain now a form of getting information from Cisco devices, it's important to notice that any station can associate to an access point or to a network without even having the credentials to do it. So management frame structure. As you can see here, the structure is pretty simple. This mark here is common for all management frames, and the body is the part where different frames differentiate between them. And this body usually have some type of fields that are fixed, like for example timestamp that is presented on beacon and proof response frames. And one of the most important fields that we have inside here are the information elements that we are going to talk a lot about in this talk, so it's important to understand what they are. So information elements are this structure. It looks pretty simple. You have 1 byte to define the type, 1 byte to define the length, and the value that it continues after the length. This is a TLB type of structure. It's really common on a lot of protocols, and it's present everywhere on management frames. But let's take 2 types of different information elements that we use every time with our phones, and maybe we don't know it, but they are used. One is the SSID information element. This is the information element in charge of putting the name of the network in the beacon frame when it's announcing it. And it's also used on the proof request frame when a station is trying to search for a known network around. So you have the type that is 0, the length that is variable, it can be up to 32 bytes, and the value of the SSID, that is the name of the network. So pretty simple structure. But what happens when a structure like this appears? Okay, this is the RSN information element. It was published on the 2004 802.I specification, and it's used for WPA networks. Okay, this is to show the capabilities of cryptography of the network on security. Okay, have someone seen something weird about this structure? Someone seen something weird? Something that makes no sense or something? No? This is a problem. As we saw before, the information element has 1 byte to define the length of the content that is inside it. But you have this type of structure inside that has 2 bytes to define a number of items inside it. So if you don't process this correctly, you will end up having a memory corruption bug. So this length nonsense that I'm putting here, maybe some people said, okay, this is obvious, anyone can see it, and it's pretty obvious. Well, there was a bug on Broadcom firmwares that affected every iPhone model and iPad model at the moment in 2012. And I found this bug that was a memory corruption in the firmware that was crashing the firmware all the time and led the device without Wi-Fi capabilities. Okay? This could be sent on a beacon frame, so every time you put your Wi-Fi enable, it crashed the firmware. The driver couldn't speak to the firmware, so the iPad or the iPhone says no Wi-Fi, and that's all. It didn't work. You can set this to any phone, or you can send it with a proof response specifically to a phone you want to do a denial of service. So you can do a denial of service of Wi-Fi to one person in particular. So this is the start of when we start seeing like structures or things that they have no much sense on the protocol. And now we're going to see a lot of more things that maybe we don't know they are there, but they are hiding. So let's talk about Cisco. Cisco is well known on the wireless market and has a really well-known equipment, IronNet, that is used for a lot of wireless networks, and it's very expensive. Okay, and the way they work to manage a really big network is you have a controller and you have a lot of access points, and this controller manage every access point you have on the network, so you can configure it centrally all your wireless network. So this is a paragraph on the Cisco CCX, that is Cisco Client Extensions documentation, and it says something funny. It says that IronNet access points will send an information element with ID number 85, and this contains the access point name, the load, the number of associated clients, and so on. We don't know what's so on. And on the reassociation response frames, that is another management frame, also unencrypted, it sends the management IP address of the controller and the IP address of the access point. So this is sent on a management frame, so anyone can see it, and this is not encrypted, and you can have any protection you want, but apparently this is a feature, so we don't have to report it, but because it's a cool feature, I think. So let's understand first what reassociation response are and how they are used. So let's suppose you are moving around with your station. Let's say a station is your phone, and you're moving around a place with a lot of access points. Well, your phone, every time you're moving towards an access point that has a stronger signal, he's going to reassociate to that access point. So he can always have the best signal on the network. That is really common. I think that everyone here use Wi-Fi during the conference. So every time you move around, your phone or your device is doing reassociation all the time, okay? Because you're moving around and you're getting to a nearest access point. So we need to get the reassociation frames to get the IP addresses of the internal network, I don't know, in the management frame. So maybe it's hard to explain, and my English is not the best, but this has no sense. They are leaking, or they are giving us internal IP addresses of the network in management frames with no encryption to anyone. You don't even have to associate to a network. It's like you do passive monitor traffic analysis, and you get this. So, well, as we can see here, this is a beacon frame from a Cisco IronNet, and we know that because it says that it has the Cisco IronNet information element here. And we can here see the name of the access point and the clients that are associated. This is sent every 100 milliseconds. Every beacon has this information of the network, okay? So let's suppose I want quickly know what is the most interesting access point to attack. I walk around a place, I get every beacon from every access point, and I say, okay, this access point has 200 clients, and this one has 2 clients. What is the most interesting to attack? This one with 200 clients. So this information is given to us free, okay, on every beacon frame. Then we have the reassociation response, okay? If we want to get the IP address, this is a little bit harder, because the problem here is that in the specification, it says that if you want to get in the reassociation response frame the IP address, you have to send a reassociation request frame with 2 information elements of Cisco. Usually your phones or the computers don't send this because they don't have the Cisco extension installed, or you don't have a specific software to do that. So if you are doing passive analysis, you're not going to get this, okay? But what if we start sending like fake frames? I send a reassociation frame with a fake MAC address to a network. This shouldn't work because we haven't been associated to a network. So if I send a reassociation request frame without being associated before, it should fail this. Well, it doesn't fail, it works. So sending one fake frame, we can get the IP address of the controller, and we can get also the access point name, everything with one frame, okay? I'm gonna show, I couldn't do the demo here because there are not Cisco access point nearby, and I didn't bring one. So I'm gonna show you a sample that I get from walking around the street here in Vienna. As we can see here, we have a BSSID of an access point, the SSID, the channel, the type of security, in this case is open, the number of the access point, the number of clients, and the IP address. I changed it a little bit, the IP address, so I didn't get in trouble. But this is a feature. Always remember, this is a feature, so it's not an attack. I'm not attacking. I'm only using a feature of the IronNet devices. As you can see here, you can see 1, 2, 3, 4, 5 access points, but in the real thing is the same access point. As you can see here in the name, this L is LWAP 015. That is the name of the access point. And these 5 networks are announced by the same access point. And as we can see here, we have 4 protected ones and 1 that is open. So maybe I want to attack this network, or maybe this one, and I can connect to this network and see what I can do from there. So they are leaking information of the internal network, like in the management frames. For me, this has no sense because they shouldn't do that. I don't understand how this can be a feature if anyone can access this information. So let's talk about Wi-Fi Alliance. Wi-Fi Alliance is an organization that does a specification for new protocols, and also it does a certification of devices. And this organization has 2 main specifications that I assume that many of you have on your phones and maybe on such other device on your home or office, but maybe you don't know about it. One is Wi-Fi protected setup, that is known for many people because it has an attack that is called the PIN brute force attack. And the idea behind this specification was to make easier the process of securing a Wi-Fi network. It did it really bad, really wrong, and they end up doing it easier for an attacker to get access to the network instead of doing the process of doing it, the network secures easier. So besides this attack, that is the PIN brute force attack, that I'm not going to talk about, this specification is enabled in a lot of devices, okay? And as we can see here in this proof response frame, remember a proof response frame is the frame when you are scanning for networks, when you enable on your phone or in your computer Wi-Fi, and you go around, you send pull request frames to see what networks are around, and the network will reply with a pull response frames with the capabilities of the network. In these frames, we can see that the WPS information element has a lot of information of the device, like the manufacturer, the model, even the serial number of the device. Again, this is not useful for the protocol itself, but apparently something in the specification that vendors should do it. So this, as we can see here, in this Netgear device, if you even disable the functionality, the WPS functionality, it's going to set it to not configure, so you are protected from attacks such as PIN brute force attack that has been discovered, I think, in 2011, but is still used today because a lot of devices are still vulnerable. But your device is still leaking all this information. So if you want to fingerprint a device wirelessly, it's really easy. You start listening to proof response, and you will get all this information. Okay? The model number can be used to know if a device is vulnerable in, I don't know, with a Wi-Fi driver or something, or the card. So this, they are leaking a lot of information of the device, and really easy. Something also that it's a little bit a privacy issue is that some of the devices, they give you the serial number, okay? They send you the real serial number of the device inside this frame. So anyone that is going around can get all this information and then analyze it. The serial number, remember that some vendors, when you register your device on the net to get warranty or other type of support, you put information of yourself with the serial number, so they can track you out with this. I think I'm going to be able to do a demo of this because this protocol is easier to find. Well, we are seeing some access points. For example, here a TP-Link, here one that says Broadcom, but it's a Thomson access point. Here we have the model number that appears to be fake, the serial number that it's fake. And here we have the model of this access point. All this information can be get passively, okay? You don't have to send even one frame. So again, protocols and specification giving us things that maybe we don't want to have, but they are there, okay? So let's talk a little bit about Wi-Fi Direct. That is another specification by the Wi-Fi Alliance. And this specification, it's used to connect devices between them. Let's say you want to connect two phones, and instead of using Bluetooth, that is maybe old now, you can use Wi-Fi and have a more speed to communicate between the phones and to share information. This is also used a lot on printers. There are a lot of printers around that they have Wi-Fi Direct, so you can go with your phone and print something. I think that Apple also call it AirPrint and things like that. This protocol, again, has an information element, so we can identify the device that has Wi-Fi Direct really easily, reading one information element. And besides that, here we can notice that the Wi-Fi Direct uses also the WPS protocol. So we have also a lot of information of the device. For example, this is my phone. If you have an Android device, you have Wi-Fi Direct. Okay, Wi-Fi Android from 2011 is the first one to support this protocol, and a lot of phones have it by default sometimes. And here we can see my phone serial number sent to the air. Okay, so anyone can get my phone serial number. On my phone, it's not enabled by default Wi-Fi Direct, but if I go and I'm looking for a printer or something to print with my phone, once I enable this mode, the phone starts sending these frames to the air. So if anyone is listening, they can get my phone serial number and other information like the model and other things. Even the device name. Sometimes device names are, for example, my name on the phone. So nowadays, we are getting a little bit worried about tracking, about being tracked. So we do macro randomization and other protections. But with this type of a specification, we break that, okay? Macro randomization is not going to be useful if we are sending the serial number of the device in the frame. So I'm going to show you again this. I don't have, we are not going to see peer-to-peer devices here. So I'm going to show you some samples I get from the city, okay? Here we have a Sony TV, a Samsung TV, a Philips TV, and here we start seeing printers, okay? Another printer, let me see if I find, here is a Roku for a media player, and here we have a guy that was, I don't know why, he have the Wi-Fi Direct enabled on his phone, and the name of the phone is the name of the person, okay? So with that information and the serial number, and you can be trackable really easily. So we're going to talk a little bit more about nonsense. As I mentioned before, length nonsense was something that it's in the protocol or in some specifications. We can see endianness nonsense also, because Wi-Fi Direct and WPS are two protocols developed by the same organization, okay? But in one protocol, they decided to use big endian. That is okay, because it's network wide order. But in the other, they're using little endian, because they wanted to change. I don't know, maybe. So this is nice, because when you send this specification to developers, if a developer doesn't read too good the specification or they miss something, they're going to have memory corruption or really bugs, because they are maybe reading something that is little endian and they are processing it like it's big endian. So again, having nonsense on the information elements. let's talk a little bit about Apple phones or Apple devices. There are two protocols. I'm not going to do a demo here because I'm like, this is work in progress, but I'm going to show you some information about it. We have two protocols here. AirPlay is one of them that is used when you want to use your Apple TV and show something on the TV or mirror your display with the TV with your Mac or with your phone, and to share music or use AirPlay enabled speakers to listen to music. Well, this is an action frame that is also a management frame, not encrypted, sent to the air from my Apple TV. And iOS was one of the first operation systems that they implemented Mac randomization, and they start saying, yes, we protect users, we don't want you to be tracked, the privacy for us is really important, so Mac randomization is implemented. This is not my real MAC address, so my device is using Mac randomization, but inside the frame, they are sending the real MAC address. So come on. This makes no sense. And it's not only sending the real MAC address, they are sending the version of my Apple TV. And it's not seen here, but it's also the device name. So if I put Andres Apple TV, it's going to say Andres Apple TV. So there are a lot of information there that could be used to fingerprint a device and to target it. There's a lot of more information here, but I'm still researching on reverse engineering the protocol because it's a private protocol. Then we have AirDrop that is similar to Wi-Fi Direct, but for Mac. And you can share between two phones, images and other things. 2 years ago, a guy from Australia presented a vulnerability on AirDrop that when I sent, for example, to a phone a file and you reject it, even if you reject it, once your phone rebooted, I could install an application on your phone without any notification. So this was broken a couple of years ago, and there are still things going on here. As we can see here, this is an action frame for AirDrop, and they have Mac randomization again, but they are sending the device name here. So Jeffrey's iPod Touch, here you are. So it's really easy again to identify the name of the device. It's set for US, for example, it here says US. So you have a lot of information on frames that, again, maybe you enable your device, Wi-Fi on your device, and you know that all this information is going into the air because maybe the only feature you want to use is connect to Wi-Fi and check your emails. But this information is going around the air. So let's quickly talk about a messy implementation. This device is a Western Digital TV media player. Like many other media players, they support a lot of features so people can use it. In this case, this device has Wi-Fi Direct enabled by default, okay? But that's okay because we saw that Samsung, Philips TV, a lot of devices support Wi-Fi Direct by default, and there's always on. So it's not an issue in itself. But usually, these devices have some type of authentication or some type of notification to the user, okay? So if I want to connect to a Samsung TV, it will show something like this on the screen and say, wait a minute, this phone or this device is trying to connect to your TV. Do you want to allow or deny, okay? So this is okay. The problem with the Western Digital device is that it does nothing, okay? It stays there, you can be playing a movie, and I can connect to your device, I can read your hard drive, I can do anything I want, and you never notice about it. And this, I'm going to show you, I'm not going to be able to do a live demo because I will need another TV, and I have the device here, so if after the talk someone wants to experience the live demo of this issue, I can do it, but let's see the video. So here I have my Western Digital connected to my Wi-Fi network. So these devices are can be in dual mode. I'm now being a station connected to my wireless, and at the same time I'm a Wi-Fi Direct device open for connections. So it could also be used to pivot to a network, okay? I'm here checking that I have connectivity. My device has flash storage connected to it. Now I'm gonna show you that this is the last version. Western Digital was unable to fix this because after waiting for 1 month, they couldn't give me a contact to fix this. So this is already published, the advisory. And now what I'm gonna do is, with my computer and an interface card that supports peer-to-peer mode, and using WPA supplicant, I'm gonna connect to the Western Digital TV media player. As you can see in the image, nothing is gonna happen, okay? This, I'm running a command to search for the peer-to-peer devices. Here it finds the Western Digital media player. I'm gonna grab the MAC address, and I'm gonna run a peer-to-peer connect command with the MAC address and the mode I want to connect to the device, that is push button authentication. This is done like Samsung TVs, everyone uses this mode usually. And now I'm connecting, and that's all, I'm connected. Now I'm gonna show you that I'm gonna be able to do ping, okay, and show you that I'm connected to the device, but that's not all. Now I'm gonna use the services that the device give to me. One of the services, it has some services like you have a web server, so you can modify the device and configure it and read the credential from the Wi-Fi it is connected to or other things. But I'm going to use the Windows sharing functionality. So I'm going to connect, and I'm going to read the flash drive that is connected to the device. And then I'm going to write a file in it. So I have read and write permissions without no authentication, neither notification. So you could be seeing a movie here and you will never notice that this is happening. So I wrote a file here. I'm reading the directory. Sorry, it doesn't look so good, the image, but again, if you want, then I can show you. Here, if we go to the video folder, we're gonna see that we still have only one file, and that is because the device checks for file system modification like 30 seconds, so every 30 seconds. So now we are going to start seeing blinking this light and a message here on top that is saying that something changed on the file system, and then we are going to see another file here, a new file. So that is how this feature works. So if you have one of these devices, I saw some of these on the city, throw it to the garbage. Even the vendor doesn't want to fix it, so I think you shouldn't use it. Well, let's get in the last part of the presentation. I'm going to talk about platform complexity. So platform complexity, it will talk about iOS and Android and how the protocol get complex, and it make that the protocol get complex and make the platform also get complex with the protocol. So two or three terms I have to explain before we start is MLME, that stands for Mac Layer Management Entity. This is the part of the code that handles the authentication, association, all this management frame processing is done in this layer. So we have two types of wireless cards. In our phones, in our computers, every card has to be one of these two types. One is the soft MAC, that it says that the wireless network interface only handles with the physical layer and the MAC. And the rest is managed by the kernel or the real-time OS or anything you have, okay? In the case of Android, it's gonna be a kernel module. If it was an iPhone device, it would be a kernel extension, and so on. And you have the other type of card that is the full MAC, and these are the cards that the MLME is inside the firmware. So now the firmware, that usually is a thin layer that doesn't do too complex things, it's started to turn a little bit more complex, okay? It has a lot of things. This case is, for example, the Broadcom that I mentioned before at the beginning of the presentation. The Broadcom was handling this type of information, the RSN processing of the information element was done in the firmware, and that's why the car crashes, and the OS, the only thing it can do is says, I don't have connectivity with the wireless card, so I cannot communicate because the firmware part is crashing and it not responds. So let's talk about Android architecture. As we can see here, we have the hardware layer that is the firmware. In this case, I'm talking about devices such as Nexus 6 or Nexus 5 or some other devices. Usually Broadcom have full Mac interfaces. Qualcomm usually use more of soft Mac interfaces. And then we have the kernel that also has a kernel module development usually by the vendor of the wireless card, in this case Broadcom. And then we have the WPA supplicant and the Android framework. So when you turn on your wireless on your phone, on your device, all these layers are doing something with the traffic, okay? So to get those little names on your screen saying, I have found an open Wi-Fi, all these layers have to do something with that information. So I'm gonna tell you some things I've done or tips I can recommend you if you're interested on looking more into the different layers. If you're gonna see firmwares of wireless cards, usually full Mac, usually you don't have symbols, nothing, it's a bare metal binary, and if you throw it, I don't know, to EDA Pro or some type of tool to disassemble it, you're not gonna have a loader or nothing, so you're gonna see like code and nothing more than code. And if you don't know what architecture is the microprocessor that is inside the wireless card, it's really hard to identify what is going on and to analyze what code it's running and how to analyze it. So that is so you can do like analysis of the kernel module, because besides full Mac network cards, in the kernel module they are like a thin kernel module. They usually don't do too much of the work because the firmware is doing a lot of the work. But if you check on the kernel, you usually got information about what chipset it is or what type of architecture it is. So you should do an analysis of the kernel and the firmware together to understand the complete context of the architecture. And in the kernel side, the advantage we have is that you can do kernel debugging on Android. I haven't done it myself, but I read some people that have done it. And or you can also use debug parameters on the kernel modules to get information about what's going on in the kernel. Then WPA supplicant and host APD, they are open source projects, so we can do source code auditing or we can debug it because they are user space. So it's easier to look into this than to kernel and firmware. And finally, the framework, again, open source. Debugging and log analysis are the best way to go there. Before getting to iOS, I'm gonna show you, let me see how much time I have. I'm gonna show you another demo. I hate to do live, I hate to do video demos or demos and show you information here. I would prefer to do live demos, but getting the devices here or doing this, it's not so easy. Sorry about that. So I will show you this vulnerability that I also found on 2014. This vulnerability was on between the last two layers of the platform. It was between the supplicant and the framework, okay? So I found a bug that when you send a malformed Wi-Fi Direct frame, the frame goes to the firmware. The firmware says, I have nothing to do here, and it forwards it to the kernel. The kernel says, okay, I forward it to the supplicant. And it's important to notice that a lot of, here we are involving different types of phones, different type of firmwares, and different type of kernel modules. So it's not like one vendor is ignoring a malformed frame. It's several vendors, when they receive some frame that they don't understand, because the protocol is so complex, sometimes they say, okay, I don't understand this frame, but maybe this is handled by someone else because it's a new protocol. So I will forward to the next guy to see what is to see what he can do with it. So they send this malformed frame through these two layers, and they send it to the supplicant. The supplicant, it couldn't handle it too well, so it sent an event to the framework that it was again broken. Okay, so the event that it was broken, the framework didn't know how to handle it. The framework threw an exception. The exception was not handled by anyone, so the Dalvik VM crashed. Okay, so with one frame, we crashed the Dalvik VM. So, as we can see here, I'm sending the frame. The frame is going to be processed first from the Motorola that already rebooted. Then the Samsung 3 is going to process the frame. Remember that when you are scanning, they are changing the channels all the time. So it depends on what channel I'm injecting. So the device is getting so it could get first on one device, then on another. The timing is different for every device, okay? But we reset it 3 devices with 1 frame, okay? Again, here we are taking the last layer of the platform, okay? So remember, the problem here is the complexity of the protocol is getting these things done, because firmwares are saying, okay, I have this frame I don't understand, but maybe the kernel module is going to handle it. So I'm going to forward this. And we start seeing all these crappy things on the protocols. Let's finally talk about iOS. iOS is pretty similar in the architecture to Android. We have the Broadcom firmware, we have the kernel extension, we have a Wi-Fi ID that is similar to the supplicant, and finally the framework. The firmware is the same as we talk on Android, so nothing different here. The kernel extension, if we want to analyze it on iOS, it was pretty difficult up to iOS 10, because the IPSW file has the kernel encrypted and the file system encrypted. From iOS 10 to now, it's unencrypted, so it's easier to analyze and do a static analysis on iOS now. So thank you, Apple. And we also are you could also be interested on checking out the kernel extension on the iOS and comparing it with the OS X, okay? Because there are shared code between them, and in OS X we got symbols. So if you want to help yourself, you should compare between them. Then when the Wi-Fi ID, that is a user space application. So if you have a jailbroken device, you can debug it. You have to be careful because it not only handles 802.11, it handles Bluetooth and I think some telephony features. So you have to be advised about that. And finally, the framework, that is a private framework, so we don't have information or documentation, and we have to jailbreak our device to use it. In Android, it's much easier. If you see the documentation, you can interact with the supplicant using the Android framework really easily. We can request to get like the wireless networks around us. We can send frames in some obscure ways, but we can do it, okay? And finally, some conclusions, because I'm getting out of time. So conclusions are that specification and proprietary protocols could help device fingerprinting. We have seen that with CCX, with AirDrop, AirPlay, Wi-Fi Direct, WPS. All these protocols can be used to fingerprint devices and understand what they are running, what type of device, what type of manufacturer they are. Specification and proprietary protocols could break privacy features such as background randomization. That is a clear example with the AirPlay that we saw, and with Wi-Fi Direct and the serial number. That is also another example. Bad implementation could expose devices to unauthenticated access. This is the case that I show of the Wi-Fi of the Western Digital TV live streaming media player. And finally, protocol and platform complexity could lead to vulnerabilities. So if the protocol gets too complex, it's going to get more features, but more code. More code with more complex protocol, it's going to lead us to different type of vulnerabilities. I show these two that I found, one on the firmware, and the other one on the framework and the user and the WPA supplicant layer. Okay. Future work: research other platforms and vendors, implement Apple Bluetooth low energy scanning protocol on Bluetooth device. I haven't mentioned this, but Apple devices, when they are scanning for other AirDrop devices or AirPlay devices, they use Bluetooth and Wi-Fi combined. So to get really a tool that is able to search for devices, I have to use Bluetooth and Wi-Fi. And Bluetooth is not it's again a proprietary protocol above Bluetooth low energy. So I have to do something with the Bluetooth firmware to get that running. And finally, develop a 802.11 information gathering tool. I'm in process of that. In fact, if you're interested, here is the project repository. I committed the code 2 days ago. So you can get this with any monitor, with any network card that has monitor mode in capabilities. You're going to be able to use these tools, and you could get CCX information, Wi-Fi Direct, or other type of information. One more thing. Also, I didn't mention this, but the other day I noticed that this. When I was walking around the city, I saw a lot of printers. We have one here in the hotel. It's a printer that says HP printer and a number. These printers, you buy it, and they have an access point on it, and it's enabled by default. If you get near, you connect without credentials usually, and you can get a lot of information of the printer and send like 1,000 copies of something to print. So these devices are I think that this is a problem that we should start analyzing, because they put Wi-Fi to everything and they don't measure what are the risks with these devices. Thank you for listening to me, and that's all.
So, thank you. Are there questions? Yes, there are.
I had a question about the CV bug for the iPhone for a crash of the driver.
Yes.
Was this permanent, or you could restore it when you reboot the device?
No, the firmware crashes every time and restart it all the time. And if you're still sending the frames, it will still crashing.
As long as you send the frame.
As you send the frame, but once you stop sending the frame, it didn't happen. But one interesting thing was that once I lived I think I was an iPad for 2 hours with this running because I was doing another thing. And when I stopped the attack, the card was never again able to get up. So I have to turn off the device to get the interface again. So.
And it's still also for me, I don't know why they're sending all the information over the management packets, like the network IP of the management access points. That makes no sense.
Yes, I don't know. It's a feature.
So, are there more questions? So, no, but a question from my side. What do you think about all the stuff that's now coming with the closed firmwares from FCC regulations and the EU regulations that you're not allowed to update the firmware on the Wi-Fi chips?
I think that it's not a good way of doing so taking decisions. I think that is not the correct way of doing things. But I know TP-Link is one of the first of major vendors that have decided to stop supporting OpenWRT or other firmwares, open firmwares. And I think that is a problem from one side because we are not going to be able to take control of our devices. But on the other side, I think we are going to see a lot of internal developments or proprietary things that they are going to put instead of using already things that they are in the open source community. So maybe we're going to see more bugs and problems on that side.
Okay. More questions? No? No? Then thank you.
Thank you.